This is an explanation of infinite series and convergence. So first, let me start with a little vocabulary and try to see if I can clarify a few things. You've got a sequence, a series, and a sequence of partial sums. Now, as an example, if we have this sequence with an nth term 2 to the n minus 1, our sequence would have the terms 1, 2, 4, 8, and so on. It's an infinite sequence. Our series then would be 1 plus 2 plus 4 plus 8, and so on. And to get the sequence of partial sums, the first partial sum is taking the first term of the series, so that's 1. The next partial sum is taking the first two terms, so 1 plus 2 is 3. Then you have 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8, and so on. And the infinite series is associated with the sequence of partial sums. It's associated with the sequence of partial sums in that if the sequence converges, the series would converge. If the sequence diverges, the series diverges. And so there is a corollary between the two. So here we have a sample infinite series. Here's our sequence of partial sums, these terms over here. And this is what I just summarized as far as how the nth partial sum, if it converges, then so does the series. And if it diverges, then so does the series. Okay, here's some sample series. We have 1 over 2 to the n. Here's some terms of that series. These are some partial sums, so first term's a half, then the next term in the sequence of partial sums is a half plus a fourth, 3/4, half fourth, eighth, 7/8, and so on. And that can finally be rewritten, this nth partial sum is 2 to the n minus 1 over 2 to the n. And as n goes to infinity, this is equal to 1. So therefore, the series converges, and it equals 1. So not only does the series converge, but we also know it equals 1. As we'll see, there's not many series we know what they converge to easily, but this being a geometric one is one of them. This next series is called a telescoping series, this one in part B. And what happens here is that you list several terms, and you realize that the negative a half and the half cancel, negative a third and third cancel, and so on, and this would be your last term, and everything would cancel out except for this first term 1 and the last term minus 1 over n plus 1. So this is a formula for your nth partial sum, and as n goes to infinity, this will go away, so you just get 1. So this is again this telescoping series, which we generalize down here, that you can find the sum relatively easily. Now for this last series, this is just the series 1, so every time n goes up, you just keep having 1s, you keep adding. So clearly this will diverge, it goes off to infinity. And you can also see that the nth partial sum is just n, because the first is 1, the second is 1 plus 1 is 2, the third is 1 plus 1 plus 1 is 3. And so this diverges because your sequence diverges. Okay, here's another example of a telescoping series. For telescoping series, oftentimes you have to get it in do partial fractions to separate it into your two pieces. So first thing we do is factor, and then we do partial fractions, decomposition to get to here. Then you start listing terms, and as you list terms, you see that which ones will be canceling out, and you're left with this first one and this last one. So this is your nth partial sum. So then as n goes to infinity, this piece will go away, and you're just left with 1. And so this series converges, and it converges to 1. Here's your geometric series again that you've dealt with the past several years. If your common ratio is between negative 1 and 1, then it will converge. If it's greater than or equal to 1 or less than or equal to negative 1, it will diverge. If it converges, this will be its sum right here. And here's an example of a geometric series 3 over 2 to the n. So we can rewrite this as 3 times half to the n. Your first term is 3 because that's 3 times half to the 0. Your common ratio is a half, so you plug it in your formula and it converges to 6. This geometric series 3 halves to the n. 3 halves is bigger than 1, therefore it diverges. Here we have a geometric series for a repeating decimal. Well, one way to do this is to realize the first term is 8 over 10 squared, and then the common ratio is always 1 over 100 if we just look at these next terms, and so you can use it as a geometric series. But here's another way to go about it that you may have seen some years ago, and that would be this idea right here. So here's a repeating decimal, 0.075, and the 75 is repeating. Because there's two decimals, you multiply by 10 squared, so you get 100. X is equal to all this. You just move the decimal place over twice. Then you subtract, so all the repeating stuff cancels. You get 99x is 7.5. And then you just divide, so x is 7.5 over 99. Now, you could also use the method shown in the example in the book, write out a few terms, and then you write it as a geometric series. Here's your first term over 1 minus r, and of course you get the same thing either way. Okay. So, as I said, there's not actually many series that you can find the sum for easily. Geometric and telescoping are two of them. Mainly what we want to end up doing in this chapter, at least the first half, is just finding out if the series even converges or diverges at all. And so the very first test we have for that is called the nth term test. And the nth term test is simply stated here. If you take the limit as n goes to infinity of the nth term of a sequence, and it does not equal 0, so not a sequence of partial sums, but the nth term of this general term of the sequence, it doesn't equal 0, then we know this series diverges. And this makes sense because if it doesn't equal 0, that means you're always adding something. And if you're always adding something on, then clearly your series is not going to stop at some finite number. It's going to go off to positive or negative infinity. So if the nth term doesn't equal 0, it diverges. But what's really important about this is that this is only a test for divergence. It's not a test for convergence. That is, if the nth term equals 0, that does not prove convergence. It's just that this test fails, you have to use others. And there's a lot of series out there where the nth term does equal 0, and yet it still diverges. And we'll explore that more later. So here we have the series 2 to the n. As n goes to infinity, it goes to infinity, which is clearly not 0, so this diverges. There's another one here, n factorial over 2n factorial plus 1. As n goes to infinity, it equals a half. A half is not equal to 0, so it diverges. This series is called the harmonic series, 1 over n, and as n goes to infinity, this goes to 0. But that does not prove convergence. It just means that the nth term test for divergence fails. And as we will actually see later, this test diverges. We'll explore that later. So, getting back over to a couple more examples. Here we have this series n plus 1 over 2 to the n minus 1. You take a limit of that nth term, and you get a half, which is not equal to 0. Therefore, it diverges by the nth term test. And 2 to the n over 100n. Take a limit as n goes to infinity. You get infinity over infinity, so you have to use L'Hopital's rule. And then you take as n goes to infinity, and you get infinity, which is not equal to 0. So this will diverge by the nth term test. If it had equaled 0, it would not necessarily converge, though. It just means the nth term test fails. A little bit more I wanted to show is some syntax. So as far as the calculator goes. So if we have this series here, which is actually called the alternating harmonic, and for this one, its numerators keep getting bigger by 1. It's alternating, it changes sign. If you want to graph that in your calculator, that sequence of partial sums, you can put it in y equals in this format, sum sequence negative 1 to the t minus 1 over t, comma, 1, comma, x. T is your counting variable, so it appears here as well, and you're going from 1 up to some value x, however many you want it to show. The calculator will go pretty slowly when it does this, though. It takes a lot of computational power. Or you can use the stat menu. So you do stat edit, and then go up to the top of L1 and type this in. This will give you the first 20 terms of this as a sequence. Then if you go to L2 and go to the top and do cum sum L1, it will output 20 rows, which would be the first 20 of the sequence of partial sums. So that'll give you just the first 20. And it turns out that this series is equal to ln 2, natural log of 2, but we're going to have to do some further studies to verify that.